Good morning. Welcome to another edition of Chemistry on the Fly with Mr. F. Today we're going to talk about 7.35, the chemistry of proteins. Okay, we already talked about that there's three different types of foods and drinks that we had. Yesterday we talked about carbohydrates. Proteins is what we're going to address today. And then next week we're actually going to hit fats and lipids. So let's review a little bit about proteins. First of all, proteins, these are the foods that we find proteins in: fish and eggs and poultry and pork and red meat, nuts, vegetables, cheese, and tofu are all some of the things that we would find in proteins. Okay, there's a whole bunch of things that proteins do. These are kind of the workhorse of our bodies. They do all kinds of things, and you can see the list here. I'm not even going to go through them again. And the role is to support the growth and maintenance of all parts of the body. They're kind of the workhorse. And we're going to say this a couple times today, but proteins are made up of long chains of amino acids. And we've talked about this before, but the potential energy for proteins is 4 calories per gram. Now we're going to take a little break and talk about something called a functional group. Now we've mentioned these a little bit in the past, but we didn't really call them by name, but we're going to give them some names now. And these are functional groups, are a group of molecules that when they attach to a molecule, a bigger molecule or another molecule, they give that other molecule certain properties. And we'll see that with our proteins today, or actually our amino acids today. Now, some of the things that they do, if they're polar, then they will often give hydrogen bonds. And when we have hydrogen bonds, we're going to pick up a new word today. Hydrophilic means it's going to be water-loving. Remember, water is also polar, and it's actually going to be attracted to another polar molecule, and it's going to create hydrogen bonds with that. And hydrophilic means that it's going to love water. Now, hydro is water. We've heard that term before, but philic actually comes from a Greek word. And if you think of philic, like Philadelphia is the city of brotherly love, that's where I grew up. You hear the base of Philadelphia is Phil, and that's also the same as loving. So that's where the word love comes from, in the city of brotherly love. And that's where philic comes from. So we have hydrophilic, and then the opposite is going to be hydrophobic. And that's when we have functional groups that are nonpolar, and these are when we have even sharing of the electrons, so there's no one that's stronger than the other. That's why something's polar, because it was oxygen most of the time is much stronger than other things, and that gives it the polarity. But nonpolar things, when we have equal sharing of electrons, and these are often hydrophobic, which means water hating. So these are ones that are not going to dissolve in water. So we have hydrophilic is water loving, and hydrophobic is going to be water hating. And then we have two other types, and there's other things as well. There's actually another set that we're not really going to address here. But these are where they give up hydrogen ions, and this is going to make something an acid, or at least that amino acid and acidic properties. And then the other one is going to be where they take on hydrogen atoms or ions, and they actually become basic, which would be the opposite of acidic. So let's look at some of the functional groups. So here's a little table for us, and we're going to look at 6 of them. The first one we're going to look at is hydroxyl, and we call them, just would say, a hydroxyl group. And then you can see the structure here is going to be a hydroxyl group has an R, which means that that's just it's called a radical group, but all that means is it's going to be it's attached to a chain of hydrocarbons. So we talk about this R, you'll see R in all of these, and all that means it's just a group of hydrocarbons, and it's attached to something, and we'll see it's going to be attached to a amino acid or other things later. But the structure for a hydroxyl group is just a oxygen and a hydrogen atom. And this is going to be just like in water. This is going to be polar. It's going to create hydrogen bonds. It's going to be hydrophilic, means it's going to love water. And then we have, when we add an OH to something, it often becomes an alcohol, or we call it an alcohol. So even when we get to fuels, we would talk about methane, and then if we add an OH in, it would be methanol. And we get that. We'll see that a lot in some of our fats as well when we get to that, and even in some of our things a little bit later today. The next one we're going to talk about is a methyl group. Now, this methyl group is a carbon with 3 hydrogens, and this is nonpolar. Carbon and hydrogen have about the same electronegativity, so they're both equal strength. So these are going to be nonpolar, and they're going to be hydrophobic, which means they're going to be not liking water. And then we have an amino group, and this is where we see a nitrogen with 2 hydrogens, and these are actually going to be wanting to remove hydrogen ions, and these often make, if we have an amino group on something, that's going to make them somewhat basic. Okay, here's our table for the next 3. The next one we're going to talk about is a carbonyl group, and this is different in that it's carbon, and it's going to be somewhere within a chain, and so that's why I have 2 R's on this one instead of just be part of the exterior part of the chain. This is going to be within a chain, and you will see that we have a double bond with an oxygen. So the oxygen is going to be double bound with the carbon, and that's going to make it somewhat polar. Oxygen is still stronger than carbon, and it's going to create some hydrogen bonds, and it's going to be hydrophilic. Now this one is actually a combination of a hydroxyl group and a carbonyl group, so it's actually, the name kind of shows that. It's called a carboxyl group. Instead of an N, it's an X in there, so it's carbon and a hydroxyl group, or carbonyl and a hydroxyl group. And we have, these are actually going to be creating acids. These are going to release that hydrogen on the hydroxyl group there, and it's actually going to become acidic. And the last one we're going to talk about, we've talked about this before, but this is a phosphate group, and we saw this in ATP. And this is going to releases hydrogen ions. It becomes acidic, but within the bonds, and we saw this within ATP, is our discussion about ATP, is that it stores energy within the bonds. So this one we won't really address much more today, but I just wanted you to realize that these are some functional groups. Now these aren't all of the functional groups. There are others, and they get crazy names, but these are the ones that we're going to see and address most often. And we've already seen some of these. If you remember, our glucose molecule had a whole bunch of hydroxyl groups sticking off the side of it. And that would make it, remember, that's going to be hydrophilic, so it's going to create, or it's going to be polar, and then it's going to kind of have hydrogen bonds that bond it together. All right, so we're going to talk about amino acids. Now, these are, again, the building blocks of proteins. And one of the interesting things that I researched is that there are only 20 amino acids needed to synthesize every protein in our body. So we have to realize that proteins aren't just 1 or 2 amino acids put together. They're probably chains of hundreds, and I don't know if it goes as far as thousands, but all of these amino acids are chained together, and they all have a purpose, and you will learn a lot about that next year in your biology class. But there are only 20 amino acids needed to synthesize. We're going to look at a couple of them. We're not going to spend time looking at all 20 of them. It doesn't make sense to do that. But let's look at how an amino acid is broken up or is built. Okay, and they're still the building blocks. So we're going to have a base and carbon and hydrogen, and you can see the carbon has 4 bonding spots, and hydrogen takes up 1 of those, and this carbon is actually called the alpha carbon. So the alpha is, I'm going to put the alpha in the middle there, and that's going to be the alpha carbon, kind of like the base of the amino acid. Okay, and then we're going to stick an amino group on one end of this, and remember, this is going to be removing hydrogen, so this is going to be a basic side. And then on the other side, we're going to put a carboxyl group, and this is going to be slightly acidic. Now, if we look at amino acid, we have amino group on the left-hand side that gives it the amino, and then on the right-hand side, we actually have an acid. So we're talking about an amino acid here. That's where the amino acid term comes from. And then we have one more connection And that's going to give us the ability to put something called a side chain in. And a side chain is really what's going to give the amino acid its properties. So here we go. We're going to make this a methyl. We're going to put our methyl group in there, which is a carbon and 3 hydrogens. And when we do this, this actually amino acid has a name, and it's called alanine. And as a result of the methyl group putting in there, alanine is going to be a nonpolar hydrophobic. So when we see this amino acid, it's going to not be wanting to be around water. Okay, so let's look at a second one. Okay, we're going to keep everything else the same. We have the amino side on the left. We have the alpha group in the middle, or alpha carbon in the middle with a hydrogen. And then we have our carboxyl group that makes our amino acid. And this time we're going to make a different one. We're going to make cysteine. Now, we talked about cysteine in a previous episode. And this is slightly polar, and it's going to be slightly hydrophobic. I picked this one because this one's a different one, and it actually has sulfur in it. We don't see sulfur all that much. Remember when we were talking about the chemistry of the body? That is in schnapps, but it's only a 0.3%, so it's not very much. But this particular one does have a sulfur in it. So this one has, it's called a methyl bridge, and then we have a sulfur with a hydrogen on it, and that's called a thion, and I'm not going to worry about memorizing that. But this one is going to be slightly polar, and it's going to be slightly hydrophobic. Now, why is it slightly polar? It's because the sulfur is nowhere near as strong as the oxygen compared to the hydrogen or the carbon that it's attached to. So it's not going to have the strength that oxygen has. So it's going to not be able to to draw those electrons away from the other things as easily. So that's why it's only slightly polar. Now we're going to talk about how do we put these guys together. Well, they're going to be called peptide bonds. So we're going to bring our two amino acids back together here. So there's alanine, there's cysteine. Okay, and then what we're going to do is we're going to see how this happens. So the first thing that happens is we're going to break the bond, and our OH is going to come off of the alanine of the carboxyl side, and it's going to match with one of the hydrogens on the amino side and create water. And then we're going to have a bridge or a bond between the two, and this one's actually called a peptide bond. So you can see that these two bond together. Now that's called a peptide bond. Now that would be a dipeptide, which means just two amino acids put together. But again, proteins are very, very long chains of amino acids. And if you want to see a video of some proteins in action, I found a really cool video that talks about a lot of the different properties, and it actually shows them more real than just the stick diagrams that I was showing. Here's the link for it, and I'm going to add this link to our video, our link today. And here's broccoli, and there is protein in broccoli. So eat your broccoli, stay safe and strong, and as always, have a great day.